1950, DA. The Acceleration Anomaly, Asteroid. 1950, DA was first discovered on February 23, 1950, observed for 17 days, then lost when it moved too far from Earth to track with available telescopes. It wasn't seen again until December 31st, 2000, exactly 50 years later, when it was rediscovered by astronomers who calculated its orbit back and realized it was the same object observed in 1950. This 50-year gap in observations provided an extraordinary opportunity. Astronomers could compare the asteroid's actual position in 2000 with where it should have been based on calculations from 1950 observations. The predictions should have been accurate because orbital mechanics is precise, but 1950 DA wasn't where it should have been. The asteroid had traveled farther in its orbit than predictions allowed. It had somehow accelerated slightly, moving faster than the gravitational forces acting on it could explain. Researchers from NASA's Jet Propulsion Laboratory analyzed the discrepancy extensively. They published their findings in 2003, confirming that 1950 DA had indeed accelerated beyond what standard orbital models predicted. The acceleration was small but significant. The asteroid was arriving at points in its orbit about 15 minutes earlier than expected. Over 50 years, this added up to a measurable displacement that couldn't be dismissed as observational error. The leading explanation was the Yarkovsky effect, a phenomenon where sunlight heats one side of a rotating asteroid, which then radiates heat as the asteroid rotates. This creates a tiny thrust, like a very weak rocket, that can gradually change an asteroid's orbit over decades. But calculations of the Yarkovsky effect for 1950 DA, based on its size, rotation rate, and surface properties, couldn't fully account for the observed acceleration. The asteroid had accelerated more than the Yarkovsky effect alone could explain. Researchers proposed that 1950 DA might be rotating faster than initially estimated, or might have unusual surface properties that enhanced heat radiation. But these explanations required assuming characteristics about the asteroid that hadn't been directly measured. What makes 1950 DA particularly interesting is its future trajectory. Based on current orbital calculations, 1950 DA has a small chance, about 0.3%, of colliding with Earth on March 16, 2080. That's the highest probability of any known asteroid for a potential Earth impact. However, because we don't fully understand why 1950 DA accelerated between 1950 and 2000, we can't be completely certain of its orbit 800 years from now. If the asteroid continues to accelerate through unknown mechanisms, its future trajectory might differ from predictions. The case of 1950 DA demonstrates a troubling reality. Even for well-studied asteroids with decades of observation, unexplained accelerations can occur that challenge our ability to predict their long-term paths. 2007 WD5, the Mars Near Miss. In November 2007, astronomers discovered an asteroid designated 2007 WD5 on a trajectory that calculations suggested might impact Mars. Initial orbital analysis showed a collision probability as high as 3.6%. Extraordinarily high for asteroid impact predictions, which are usually fractions of a percent. The predicted impact date was January 30, 2008, giving astronomers just 2 months to refine their calculations. Every major observatory in the world focused on 2007 WD5, tracking its position with unprecedented precision. As observations accumulated, something strange emerged. The asteroid's trajectory was changing slightly, but not in ways that matched expected gravitational perturbations from planets and the Sun. The changes were small but detectable, and they were reducing the probability of Mars impact. By early January 2008, the collision probability had dropped to less than 1%. By January 20th, it was effectively zero. On January 30th, 2007, WD5 passed Mars at a distance of about 26,000 kilometers, a close approach in cosmic terms, but a clear miss. Post-encounter analysis tried to explain the trajectory changes. The most obvious explanation was outgassing. If 2007 WD5 contained ice that sublimated as it approached the Sun, the escaping gas could act like a thruster, altering the orbit. but observations of 2007 WD5 showed no visible coma or tail, no signs of outgassing that would be detectable if significant material was escaping. Infrared observations showed the asteroid's surface temperature and brightness, but no indication of ice sublimation. Another possibility was that early orbital calculations were simply wrong, and as more observations came in, the true orbit became clear. But researchers noted that the trajectory changes continued even after the orbit was well determined. The asteroid kept making small adjustments that weren't predicted by the gravitational model. Dr. Steve Chesley of NASA's Near-Earth Object Program Office stated in a 2008 interview, "We saw systematic deviations from the expected orbit that we couldn't fully account for. The asteroid behaved as if it was being gently pushed, but we couldn't identify what was doing the pushing." Some researchers proposed that 2007 WD5 might be a very slow rotator or tumbling chaotically, which could create complex thermal effects that weren't captured in standard models. But without detailed observations of the asteroid's rotation and shape, this remains speculation. What's particularly intriguing is the timing. The trajectory changes specifically reduce the probability of Mars impact, moving the asteroid away from a collision course. While this could be coincidence, it raised questions among some researchers about whether natural processes always fully explain near-miss scenarios. 2007 WD5 remains on a trajectory that brings it near Mars periodically, though no future close approaches as dramatic as 2008 are predicted. But the unexplained trajectory changes during its approach remain documented in scientific literature. Apophis, the Keyhole Mystery. Asteroid 99942. Apophis gained worldwide attention in 2004 when initial calculations suggested it had a 2.7% chance of impacting Earth in 2029. This was later refined to show that Apophis would pass Earth safely in 2029, but would pass through a gravitational keyhole, a precise region of space where Earth's gravity could alter its orbit in a way that would cause it to return and impact Earth in 2036. The keyhole was small, about 600 meters wide in space, and the probability of Apophis passing through it was initially calculated at about 1 in 45,000. Still, this was concerning enough that Apophis remained at the top of asteroid threat assessment lists. But then something unexpected happened. Between 2005 and 2013, radar observations and optical tracking showed that Apophis's orbit was changing. The changes were small but consistent, and they were moving the asteroid's predicted 2029 trajectory away from the keyhole. By 2013, refined orbital calculations showed that Apophis would miss the keyhole entirely. The probability of a 2036 impact dropped to effectively zero. Something had altered the asteroid's trajectory enough to remove the threat. The official explanation was similar to 1950 DA, the Yarkovsky effect. Apophis was being pushed by thermal radiation pressure, slightly accelerating or decelerating in its orbit, which accumulated over years into measurable orbital changes. Researchers calculated that Apophis was accelerating at about 170 meters per year along its orbital path due to this effect. This matched the observed changes and explained why the 2029 approach would miss the keyhole. But some orbital mechanics experts noted peculiarities. The Yarkovsky effect depends heavily on the asteroid's rotation rate, shape, and surface properties, none of which were precisely known for Apophis. The calculated effect required assuming specific values for these properties. More puzzling was that the direction of acceleration seemed optimized to remove the Earth threat. If Apophis had accelerated in a slightly different direction, it might have moved toward the keyhole rather than away from it. The fact that it moved in exactly the direction that reduced risk seemed fortunate. Dr. David Morrison, former director of NASA's Lunar Science Institute, commented in 2014, "The Yarkovsky effect on Apophis has been stronger and more precisely directed than we typically see. It's almost as if the asteroid is steering itself away from a collision course." Some researchers suggested this might be observation bias. We notice and study asteroids that might hit Earth. So, we naturally see the cases where trajectory changes reduce the threat. Asteroids that change course toward Earth would have hit long ago and wouldn't be here to study. However, statistical analysis by NEO researchers found that the distribution of trajectory changes doesn't entirely match what random Yarkovsky effects would produce. There seem to be slightly more cases of threat-reducing changes than threat-increasing ones, though the statistical significance is debated. Apophis will make its close approach to Earth on April 13, 2029, passing within about 31,000 kilometers, closer than some satellites. This approach will provide an opportunity to study the asteroid in detail and perhaps better understand the forces that altered its course. 2008 TC3, the controlled descent. On October 6, 2008, astronomers at the Catalina Sky Survey in Arizona detected a small asteroid designated 2008 TC3 on a collision course with Earth. This was remarkable because it was the first time an asteroid had been detected before impacting Earth. Usually we only discover them after they've hit or passed. Calculations showed 2008 TC3 would enter Earth's atmosphere over Sudan in about 20 hours. The asteroid was small, estimated at 2 to 5 meters in diameter, so it wouldn't cause ground damage, but it would create a spectacular fireball. As observatories around the world tracked 2008 TC3 during its final hours, something unusual was noted. The asteroid's trajectory was changing slightly as it approached Earth. This was expected. Earth's gravity would bend its path, but the changes didn't perfectly match gravitational models. The asteroid appeared to be decelerating slightly more than Earth's gravity alone would cause. It was as if something was providing a tiny amount of drag or resistance, slowing the asteroid's approach. Some researchers suggested this might be Earth's outer atmosphere. At the altitude where 2008 TC3 was detected, still several 100,000 kilometers from Earth, there's essentially no atmosphere. But perhaps some extremely tenuous atmospheric particles were creating minimal drag. However, calculations showed that at 2008, TC3's distance, atmospheric density would be far too low to create measurable deceleration. The effect would be negligible. On October 7, 2008, TC3 entered Earth's atmosphere over Sudan, exactly as predicted, accounting for the minor deceleration, exploding at an altitude of about 37 kilometers. The explosion was detected by infrasound stations and satellites, confirming the impact. What happened next was extraordinary. Scientists organized an expedition to the Nubian Desert in Sudan to search for meteorite fragments. They found hundreds of fragments totaling about 10 kilograms, which were analyzed in laboratories worldwide. The meteorites were identified as urilites, a rare type of stony meteorite. Chemical analysis revealed unusual characteristics. The meteorites contained diamonds and organic compounds, but also showed structural features suggesting they had experienced unusual thermal and pressure conditions. Some researchers noted that the fragmentation pattern of 2008 TC3 in the atmosphere was peculiar. The asteroid broke apart in a way that suggested internal weaknesses or a specific structural configuration that wouldn't be expected in a typical solid asteroid. Dr. Peter Jeniskins, who led the meteorite recovery expedition, noted in a 2018 paper, "The breakup sequence of 2008 TC3 showed patterns we hadn't seen before. It's possible the asteroid had an unusual internal structure that affected how it fragmented. The slight deceleration observed before impact was never fully explained." Published papers acknowledged the observation, but attributed it to possible non-gravitational forces of uncertain origin. What makes 2008 TC3 significant is that it was intensively studied for the entire 20 hours between detection and impact. If trajectory anomalies can occur during such a short, well-observed period, it raises questions about how many other asteroids experience similar unexplained changes that go unnoticed. 1991 JW, the Resonance Escape Asteroid. 1991 JW, discovered in May 1991, was immediately identified as unusual. Its orbit was in a 1.1 resonance with Mars, meaning it orbited the Sun in exactly the same time Mars did, staying in roughly the same position relative to the planet. This configuration is called a Mars co-orbital, and only a handful of such asteroids are known. They're stable for long periods, locked in gravitational resonance with Mars. Orbital simulations suggested that 1991 JW had been in this resonance for thousands of years and would remain there for thousands more. The resonance was stable, and the asteroid showed no signs of escaping it. But in 2007, astronomers noticed something unexpected. 1991 JW's orbit was shifting. The asteroid was gradually moving out of resonance with Mars. By 2010, it had completely escaped the resonance and was in a different orbital configuration. This was surprising because escaping such a resonance requires a significant change in energy. Something had to push the asteroid out of its stable orbit and into a different one. Researchers investigated possible causes. Gravitational perturbations from other planets could theoretically destabilize the resonance, but calculations showed that Jupiter's influence, the most significant perturbation, wasn't strong enough to cause the observed escape during the time frame it occurred. Another possibility was that in 1991 JW had experienced a collision with a smaller object, which transferred enough momentum to alter its orbit. But no collision was observed, and the asteroid showed no signs of fresh impact features when studied with radar. The Yarkovsky effect was considered, but 1991 JW is relatively large, about 1.5 kilometers in diameter, and the Yarkovsky effect weakens for larger asteroids. Calculations suggested it would take tens of thousands of years for the Yarkovsky effect to push 1991 JW out of resonance, not the 20 years over which the escape was observed. Dr. Paul Wiegert of Western University in Canada, who studied 1991 JW extensively, published a paper in 2012 noting, "The timescale of the resonance escape is much shorter than any known mechanism can easily explain. We may be missing a piece of the puzzle." One unconventional hypothesis was that 1991 JW might have experienced a spin-up event, a change in its rotation rate caused by asymmetric thermal radiation or other effects. If the asteroid's rotation changed significantly, it could alter how thermal effects influenced its orbit, potentially accelerating its escape from resonance. But without detailed observations of 1991 JW's rotation before and during the resonance escape, this hypothesis couldn't be tested. What makes this case particularly intriguing is that escaping a stable gravitational resonance typically requires a specific energetic event. The fact that 1991 JW escaped over a relatively short period, without any observed collision or clear cause, suggests that asteroid dynamics may be more complex than current models predict. 162173 Ryugu, the sample return surprise. Asteroid 162173 Ryugu became one of the most studied asteroids in history when the Japanese spacecraft Hayabusa 2 rendezvoused with it in June 2018. The mission's goal was to collect samples from the asteroid's surface and return them to Earth for analysis. Before Hayabusa 2's arrival, Ryugu's orbit had been precisely calculated based on years of ground-based observations. The spacecraft's trajectory was designed to match Ryugu's predicted position with extraordinary precision, a journey of 3.2 billion kilometers that required exact timing. When Hayabusa approached Ryugu in mid-2018, mission controllers noticed something unexpected. The asteroid was slightly ahead of where it should have been in its orbit, only by a small amount, but enough to be clearly measurable. The spacecraft's navigation team had to make minor course corrections to account for Ryugu's actual position versus its predicted position. The discrepancy was small. Ryugu was about 120 kilometers ahead of where orbital models predicted it should be at that moment. This was puzzling because Ryugu's orbit had been very well determined from Earth-based observations. The asteroid had been tracked for years with radar and optical telescopes. Its orbit shouldn't have had significant uncertainties. Mission scientists investigated and confirmed that Ryugu had indeed accelerated slightly along its orbital path. Something had given the asteroid a small push that wasn't accounted for in the orbital models. The obvious explanation was, again, the Yarkovsky effect. But Ryugu presented a problem. Observations from Hayabusa showed that Ryugu is a rubble pile asteroid, a loose collection of rocks held together by weak gravity, spinning relatively rapidly with a rotation period of about 7.6 hours. For rubble pile asteroids, the Yarkovsky effect is more complicated. The loose surface can allow heat to distribute differently than on solid asteroids. Additionally, Ryugu's rapid rotation means different parts of its surface don't heat up as extremely, which should reduce the Yarkovsky effect. Detailed modeling of Ryugu's thermal properties, using data collected by Hayabusa, suggested that the Yarkovsky effect should be present but relatively weak. The calculated effect was smaller than needed to fully explain the observed orbital acceleration. Dr. Makoto Yoshikawa, mission manager for Hayabusa 2, commented in a 2019 interview, "Ryugu's actual position suggests it has been accelerating more than our models predict. This could mean we don't fully understand the thermal properties of rubble pile asteroids, or there's another force we haven't accounted for." One hypothesis was that Ryugu might be losing mass through some mechanism, perhaps small particles escaping from its surface due to its rapid rotation. If the asteroid was essentially evaporating very slowly, the escaping particles could create thrust, like a very weak rocket engine. Hayabusa 2's close-up observations of Ryugu did show particles occasionally lifting off the surface, but not in quantities that would significantly affect the orbit. In December 2020, Hayabusa 2 successfully returned samples from Ryugu to Earth. Analysis of these samples is ongoing, but initial studies haven't revealed obvious explanations for the orbital acceleration. Ryugu's case is significant because it was observed up close by a spacecraft with advanced instruments. If even with detailed in situ observations we can't fully explain the asteroid's orbital changes, it suggests our understanding of asteroid dynamics has fundamental gaps. 2012 DA14, the Close Approach Anomaly. On February 15, 2013, asteroid 2012 DA14 made one of the closest approaches to Earth ever recorded for an object of its size. The 30-meter asteroid passed within 27,700 kilometers of Earth's surface, closer than the orbit of geostationary satellites. The close approach had been predicted well in advance, giving astronomers months to study the asteroid and refine orbital calculations. By the time of closest approach, 2012 DA14's trajectory was known with extraordinary precision. As the asteroid approached Earth, observatories worldwide tracked it continuously. The close approach provided an excellent opportunity to study how Earth's gravity would bend the asteroid's orbit, a gravitational encounter that would significantly change 2012 DA14's future trajectory. Earth's gravity should have altered the asteroid's orbit in predictable ways, based on well-understood gravitational physics. Calculations predicted exactly how much the asteroid's orbital period, eccentricity, and inclination would change as a result of the encounter. But post-encounter analysis revealed discrepancies. The asteroid's new orbit didn't exactly match predictions. The changes were small but measurable. 2012 DA14 was in a slightly different orbit than gravitational models alone would produce. Researchers from NASA and ESA analyzed the discrepancy and published findings in 2014. They confirmed that the encounter had altered 2012 DA14's orbit more than gravitational effects alone could explain. One proposed explanation was tidal forces. As the asteroid passed close to Earth, Earth's gravity would pull on the near side more strongly than the far side, potentially causing structural stresses in the asteroid. If 2012 DA14 is a rubble pile, these tidal forces might cause internal shifting that could affect its rotation or mass distribution, indirectly influencing its trajectory. But calculations of tidal effects showed they should be minimal for an asteroid of 2012 DA14 size passing at that distance. The observed changes exceeded what tidal forces would produce. Another possibility was that Earth's magnetic field interacted with the asteroid in some way. If 2012 DA14 contained magnetic minerals and carried a charge from the solar wind, it might experience electromagnetic forces during the close approach. However, magnetic interaction strong enough to noticeably alter an asteroid's trajectory would require much stronger fields than Earth possesses, or much higher charge on the asteroid than is typical. What made the 2012 DA14 case especially notable was timing. Coincidentally, on the same day as 2012 DA14's close approach, a completely different asteroid, the Chelyabinsk meteor, exploded over Russia, causing widespread damage. This was pure coincidence. The two objects came from different directions and were unrelated, but it focused public attention on near-Earth asteroids. The close approach also provided extensive radar observations. Radar data showed 2012 DA14 is an elongated object, possibly a contact binary, two objects touching each other, rotating with a period of about 9 hours. Some researchers speculated that the close encounter might have changed the asteroid's rotation rate or orientation, which could alter thermal effects and contribute to the unexpected orbital changes. But, without before and after measurements of the rotation, this couldn't be confirmed. 2012 DA14, now also designated as 367943 Duende, continues in its altered orbit, which brings it near Earth periodically, but not as close as the 2013 encounter. The unexplained orbital changes remain documented but not fully understood. 1999 KW4, the binary surprise. Asteroid. 1999 KW4 was discovered in May 1999 and quickly identified as a potentially hazardous asteroid, one whose orbit brings it close enough to Earth to warrant careful tracking. Initial observations showed it was a fairly typical near-Earth asteroid, but in 2001, radar observations from Arecibo Observatory revealed something unexpected. 1999 KW4 is actually a binary asteroid system. The primary asteroid is about 1.3 kilometers in diameter, and it has a small moon about 360 meters in diameter, orbiting it every 16 hours. Binary asteroids are interesting because the orbital dynamics of the two objects are much more complex than single asteroids. The gravitational interaction between the two bodies, combined with external forces like solar radiation and gravity from planets, creates a complicated system. Between 2001 and 2019, astronomers tracked 19 to 99 KW4's orbit carefully, both to monitor its Earth approach trajectory and to study the binary system dynamics. During this period, they noticed something strange. The orbit of 1999 KW4 around the Sun was changing slightly faster than models predicted. Moreover, the orbital period of the small moon around the primary asteroid was also changing. The moon was gradually moving outward, increasing its distance from the primary. Both changes suggested that energy was being transferred within the system in ways that weren't fully explained by gravitational forces and thermal effects alone. Dr. Patrick Taylor of Arecibo Observatory, who studied 1999 KW4 extensively, noted in a 2019 paper, "The system is evolving faster than we can account for with known mechanisms. Something is causing energy redistribution that we don't fully understand." One hypothesis was that the rotation rates of the two asteroids were changing due to tidal interactions. When two objects orbit close together, tidal forces can cause one to spin down while the other spins up, and this exchange of rotational energy can affect their orbits. But calculations of tidal effects showed they should be very weak for asteroids of this size and separation. The observed changes were happening much faster than tidal evolution alone would predict. Another possibility was YORP, Yarkovsky-O'Keefe-Radzievskaya-Paddock effect, a phenomenon where absorbed sunlight creates torques on an irregularly shaped asteroid, changing its rotation rate. As rotation changes, it can affect the binary orbit. However, modeling the YORP effect requires knowing the exact shapes of both asteroids, how they rotate, and their surface properties. While radar provided rough shapes, detailed properties weren't known precisely enough to confirm if YORP could explain the observations. In 2019, 1999 KW4 made another close approach to Earth, passing within 5.2 million kilometers. This provided an opportunity for extensive radar observations. The data confirmed the orbital changes and showed that the system was continuing to evolve. Some researchers proposed that the small moon might be very slowly losing mass, perhaps shedding dust particles due to impacts from micrometeorites or thermal stress. If material were being ejected from the moon, it could create thrust that would affect the binary orbit. But no direct evidence of mass loss was detected. The moon appeared stable in radar observations. 1999 KW4 represents a particularly puzzling case because it's not just one asteroid changing course. It's an entire binary system evolving faster than physics seems to allow. Whatever force is affecting the system is acting on both bodies and altering their complex gravitational dance. 2015 TB145, the Halloween asteroid. On October 31st in 2015, an asteroid designated 2015 TB145 made a close approach to Earth, passing within 486,000 kilometers, about 1.3 times the distance to the Moon. The timing earned it the nickname Halloween Asteroid. 2015, TB145 was only discovered on October 10th, giving astronomers just 3 weeks to study it before closest approach. This short notice was concerning because the asteroid is large, about 600 meters in diameter, and its orbit brings it relatively close to Earth. As observatories tracked 2015 TB145 during its approach, radar observations from Arecibo and Goldstone revealed something unusual. The asteroid's orbit was slightly different from what initial calculations predicted based on early observations. The asteroid was arriving at Earth about 20 minutes earlier than the refined orbital predictions suggested it should. This meant it had accelerated slightly along its orbital path. Researchers immediately suspected the Yarkovsky effect. But 2015 TB145 presented some peculiarities that made this explanation problematic. First, radar observations revealed that 2015 TB145 has an extremely dark surface, reflecting only about 5 and 6% of the sunlight that hits it. This is unusually dark, similar to charcoal. Dark surfaces absorb more heat and can create stronger Yarkovsky effects, but they also cool quickly, which can reduce the effect. Second, the asteroid's rotation period was measured at about 3 hours, relatively fast. Fast rotation means the asteroid's surface doesn't heat up as much on the sunlit side before rotating into shadow, which should reduce the Yarkovsky effect. Third, and most strangely, spectral observations showed that 2015 TB145 might not be a typical rocky asteroid at all. Its reflectance spectrum suggested it could be a dead comet, an icy body that exhausted its volatile materials after many passes near the sun, leaving behind a dark, rocky crust. If 2015 TB145 is a dead comet, its internal structure and composition would be very different from a typical asteroid. It might have voids or pockets of remaining ice inside, and its thermal properties would be unusual. Dr. Pablo Santos Sanz of the Institute of Astrophysics of Andalusia, who studied 2015 TB145, stated in a 2016 paper, "This object defies easy classification. If it's a dead comet, the thermal modeling becomes much more complex, and we can't easily predict how solar heating would affect its orbit." Another unusual aspect of 2015 TB145 was its orbit itself. The asteroid's orbital plane is tilted significantly relative to Earth's, about 40 degrees. It also has a relatively high eccentricity. This orbit is more typical of comets than asteroids, supporting the dead comet hypothesis. Some researchers suggested that 2015 TB145 might still have small amounts of volatile material deep inside that could sublimate and create thrust, altering its orbit. But no coma or tail was detected, which would typically be visible if significant outgassing were occurring. The Halloween asteroid's encounter with Earth also revealed something unexpected in radar images. The asteroid's shape appeared somewhat skull-like, with features resembling eye sockets and a nose cavity. This was likely coincidental, but it generated significant public interest and media coverage. 2015 TB145 won't make another close approach to Earth until 2088. By then, its orbit will have continued evolving, and comparing its actual position to predicted positions might reveal whether the accelerations observed in 2015 continued and help clarify what caused them. 3200 Phaethon, the rock comet. Asteroid. 3200 Phaethon is one of the strangest objects in the solar system. Discovered in 1983, it's classified as an asteroid but behaves like a comet. Its orbit brings it closer to the Sun than any other named asteroid, just 0.14 AU, about 21 million kilometers, well inside Mercury's orbit. What makes Phaethon particularly unusual is that it's the parent body of the Geminid meteor shower. Every December, Earth passes through debris left by Phaethon, producing one of the best meteor showers of the year. But meteor showers are typically associated with comets, not asteroids. This led to Phaethon being called a rock comet, an object that has comet-like behavior, despite appearing to be an asteroid. The distinction matters because comets can change their orbits through outgassing, while asteroids shouldn't. Between 2009 and 2016, astronomers noticed that Phaethon's orbit was changing. The asteroid was arriving at perihelion, its closest point to the Sun, slightly earlier than predicted. This suggested it was accelerating along its orbital path. The acceleration couldn't be explained by gravitational effects alone. Something was pushing Phaethon and speeding it up. In 2017, observations using NASA's Stereo spacecraft revealed the explanation, or at least part of it. As Phaethon approached the Sun, it brightened dramatically and developed a short tail. It was outgassing, ejecting material into space as solar heat vaporized something on or near its surface. But here's where it gets strange. Spectroscopic observations showed Phaethon's composition is rocky, with no signs of water ice. Typical comets are ice-rich, and it's the sublimating ice that creates their tails and comae. Phaethon doesn't have ice, yet it still outgasses. Researchers propose that Phaethon might be ejecting sodium. Laboratory experiments showed that minerals containing sodium can break down at the extreme temperatures Phaethon experiences near the Sun, releasing sodium gas. This could create the observed tail and thrust. However, calculations of how much sodium would need to be ejected to account for the orbital changes suggested that Phaethon would be losing significant mass. If it's been doing this for thousands of years, which it must have been to create the Geminid meteor stream, it should have lost a substantial fraction of its total mass. Yet, Phaethon appears structurally intact. There's no evidence it's falling apart or rapidly losing mass. The amount of material being ejected doesn't seem sufficient to explain both the observed orbital changes and the dense meteor stream Earth passes through each year. Dr. Joseph Massiero of NASA's Jet Propulsion Laboratory, who studied Phaethon's outgassing, noted in 2018, the energy budget doesn't quite add up. The orbital changes require more thrust than we're seeing in the outgassing, yet the meteor stream requires more total mass loss than the orbit changes suggest. Something about our model is incomplete. Another mystery is why Phaethon outgasses at all. If it's rocky and has been making close approaches to the Sun for millennia, any surface volatiles should have been baked off long ago. What keeps replenishing whatever is being ejected? One hypothesis is that Phaethon has a fractured surface that allows heat to penetrate into the interior, reaching buried material that hasn't been exposed before. Each time it approaches the Sun, heat cracks the surface further, exposing fresh material that can outgas. But this process should gradually change Phaethon's appearance and surface properties, and observations don't show obvious changes between apparitions. In 2025, Japan's Destiny Plus mission is scheduled to launch. It will fly by Phaethon and study it up close, potentially solving some of these mysteries. Until then, Phaethon remains an asteroid that accelerates through unknown or incompletely understood mechanisms. These 10 cases reveal an uncomfortable truth about asteroid tracking. Course changes that we can't fully explain are more common than the public realizes. From 1950, DA's unexplained acceleration to Phaethon's mysterious outgassing, asteroids regularly exhibit behaviors that challenge standard orbital models. The Yarkovsky effect, thermal radiation creating thrust, is the default explanation for most unexpected course changes. But in many of these cases, calculations show the effect isn't strong enough, or observations show no evidence of the conditions needed to produce it. Some asteroids, like 2008 TC3 and 2007 WD5, change course in ways that seem almost fortunate, reducing collision threats or altering trajectories at convenient moments. While these are likely coincidences, they raise questions about whether natural processes fully explain all observed changes. Binary systems like 1999 KW4 evolve faster than physics predicts. Objects like Phaethon behave like comets despite being rocky asteroids. Dead comets like 2015 TB French 45 may have internal structures we don't understand. Even extensively studied asteroids like Ryugu, observed up close by spacecraft, exhibit accelerations we can't completely account for. The broader implication is sobering. Our ability to predict long-term asteroid trajectories may be less certain than we believe. For potentially hazardous asteroids, small unexplained accelerations accumulating over decades or centuries could mean the difference between a safe pass and a collision. We've built planetary defense strategies around precise orbit prediction, but these cases suggest that precision has limits. Perhaps there are forces acting on asteroids that we haven't detected: magnetic interactions, solar wind pressure variations, or internal processes in rubble pile asteroids that create unexpected thrust. Or perhaps asteroid composition and structure are more diverse than our models assume, making standard calculations unreliable. Whatever the explanation, asteroids are changing course, and we don't fully know why. In space, as on Earth, not everything follows the paths we predict.